A widening crack in one of Yosemite Valley's most recognizable granite formations has drawn unusual attention from park officials, climbers, and geologists alike. Along the towering face of Royal Arches, a fracture that was barely noticeable when first observed has continued to expand, prompting closures, intensive monitoring, and renewed focus on the geological forces that constantly reshape the walls of Yosemite National Park. Why would a crack in solid granite continue to grow after appearing seemingly out of nowhere? Why has this particular fracture attracted more concern than the countless joints and fissures that already exist throughout Yosemite's cliffs? And what does its slow expansion reveal about the powerful processes operating inside one of the world's most famous landscapes? The feature at the center of concern lies on the western side of the Royal Arches Formation near climbing routes known as Superslide, Serenity Crack, and Sons of Yesterday. The fracture was first noticed during the year 2023, when climbers reported the appearance of a fresh crack in an area that had previously shown no obvious sign of instability. Further examination revealed that the fracture had partially detached a large granite pillar from the surrounding cliff, and that movement was actively occurring within the rock mass. Park officials responded by closing climbing routes and portions of nearby trails while monitoring efforts began. The concern was not merely the existence of a crack, but the fact that the rock appeared to be moving and continuing to separate over time. By late 2025, reports indicated that the opening had expanded from approximately 1 inch, or about 2½ centimeters, to roughly 4 inches, or about 10 centimeters, across portions of the fracture. Observers documented continuing movement, unusual cracking sounds, and evidence that the detached granite pillar remained unstable. These developments prompted additional closures and reinforced the view that the area represented an active rockfall hazard rather than a completed geological event. Park personnel described the fracture as one of the most unusual currently evolving instability zones within Yosemite Valley. Understanding why this crack matters requires understanding the geological setting of Yosemite itself. The valley is often viewed as a static landscape of enormous granite cliffs, but in reality, it is a dynamic environment undergoing continuous change. The cliffs that rise thousands of feet above the valley floor are not monolithic blocks of perfectly solid stone. They are fractured, jointed, and constantly responding to changing stresses generated by temperature fluctuations, erosion, water infiltration, and the gradual release of pressure that has been acting on the rock for millions of years. The granite that forms Royal Arches originated deep beneath the surface during the age of dinosaurs when enormous bodies of molten rock slowly cooled underground. As these magmatic bodies crystallized, they formed interlocking mineral grains dominated by quartz, feldspar, and mica. At the time of formation, the granite was buried beneath miles of overlying rock. The immense weight of this overburden exerted tremendous pressure on the crystallizing rock mass. Over millions of years, tectonic uplift and erosion stripped away the rocks above the granite. As the overlying weight diminished, the granite responded by expanding slightly. Although the amount of expansion was small relative to the size of the rock body, the effect was sufficient to create extensive networks of fractures known as unloading joints or exfoliation joints. These fractures developed because the granite was adjusting to a dramatically reduced pressure environment. Royal Arches itself is a product of this process. The curved recesses that give the formation its name were created by repeated episodes of exfoliation, in which large sheets of granite detached from the cliff face. Unlike sedimentary rocks that form in layers, granite tends to fracture in response to stress release. Over long periods, these fractures become pathways for weathering and eventual rockfall. The graceful architecture visible today is therefore the result of repeated episodes of cracking, detachment, and collapse, extending over immense spans of geological time. The newly expanding fracture near Superslide appears to be associated with the same fundamental geological mechanism. Rather than representing an entirely new process, it is best understood as a modern example of exfoliation occurring in real time. What makes it noteworthy is that scientists and park officials have the opportunity to observe its evolution while it is happening. Exfoliation is often misunderstood as a simple peeling process, but the mechanics are considerably more complex. As pressure is released from granite, stresses become redistributed throughout the rock mass. Certain zones experience tension, causing fractures to propagate parallel to the cliff surface. Once a fracture develops, it creates a plane of weakness separating a slab or pillar from the surrounding rock. Gravity then begins exerting influence on the detached mass. The detached section does not necessarily fall immediately. In many cases, movement occurs gradually over months, years, decades, or even centuries. Small displacements accumulate as environmental conditions change. Temperature variations, moisture fluctuations, and seasonal cycles all contribute incremental amounts of movement. Eventually, these changes weaken the remaining connections between the detached block and the cliff. When those connections fail, rockfall occurs. One of the most important drivers of movement in Yosemite's granite is thermal expansion. Granite expands when heated and contracts when cooled. Although the amount of expansion during a single day may seem insignificant, the cumulative effect can be substantial. A cliff face exposed to intense summer sunlight can experience temperatures far exceeding surrounding air temperatures. As the rock warms, mineral grains expand. When temperatures drop during the evening, contraction follows. Scientists studying Yosemite have documented measurable movement associated with these thermal cycles. Research conducted on granite slabs at Royal Arches demonstrated that fractures can open and close in response to daily and seasonal temperature changes. During exceptionally warm conditions, crack openings may increase significantly compared with cooler periods. Over long timescales, repeated thermal cycling acts as a mechanical fatigue process, progressively weakening the rock. The significance of thermal expansion lies not only in the movement it produces, but also in the stress concentrations it generates. Different minerals within granite respond slightly differently to temperature changes. Quartz, feldspar, and mica expand at different rates. This differential expansion creates microscopic stresses along grain boundaries. Over thousands or millions of cycles, these stresses contribute to crack initiation and growth. The expanding Royal Arches fracture is therefore not simply opening because a single force is pushing the rock apart. Rather, it reflects the cumulative effects of countless thermal cycles operating across a pre-existing zone of weakness. Each hot day and cool night contributes a tiny increment of movement. Individually, these increments are almost imperceptible. Collectively, they can produce measurable separation. Water also plays a critical role in fracture evolution. Rainfall and snowmelt infiltrate existing joints and cracks. Once inside the rock mass, water alters the mechanical environment in several ways. It increases pore pressure, adds weight, promotes chemical weathering, and provides conditions necessary for freeze-thaw activity. Freeze-thaw weathering remains particularly important during Yosemite winters. Water entering a fracture expands by approximately 9% when it freezes. This expansion generates significant pressure against fracture walls. Repeated freezing and thawing gradually widens cracks and dislodges rock fragments. Even when individual freezing events produce minimal change, the cumulative effect over many seasons can be substantial. The Royal Arches fracture is exposed to environmental conditions that encourage these processes. Water can enter the crack during precipitation events, while winter temperatures periodically allow freezing within portions of the fracture system. Each cycle contributes incremental widening and further detachment of the granite pillar. Another factor influencing crack growth is gravity itself. Once a fracture partially isolates a rock mass from the surrounding cliff, gravitational forces begin acting on the detached section differently than on the intact rock. The detached block may rotate slightly outward, settle downward by tiny amounts, or flex in response to thermal expansion and contraction. These motions can enlarge the fracture and reduce frictional resistance along the separation surface. Because the Royal Arches feature involves a partially detached granite pillar, gravity likely plays a continuous role in its evolution. The pillar remains attached, but the crack indicates that the mechanical connection has weakened. Each increment of movement alters stress distribution within the remaining rock bridges that hold the pillar in place. Rock bridges are small intact sections connecting an otherwise detached block to the parent cliff. They are critically important because they bear much of the load once separation has occurred. As crack growth progresses, rock bridges become increasingly stressed. Eventually, they may fracture, leading to accelerated movement or complete detachment. Yosemite's history demonstrates that such failures are neither rare nor unexpected. The park experiences frequent rockfalls as a natural consequence of its geology. Long-term records document well over 1,000 rockfall events over approximately 150 years of observation. Many more undoubtedly occurred before systematic monitoring began. Rockfall is not an anomaly in Yosemite. It is one of the principal processes responsible for shaping the landscape. Most rockfalls occur without warning and involve relatively small volumes of material. Others involve massive slabs weighing thousands of tons. The challenge for scientists is determining which fractures are actively evolving and which are relatively stable. The Royal Arches crack attracted attention precisely because observers documented ongoing movement and widening over a relatively short period. Monitoring technologies have transformed the ability to study such features. Modern investigations employ laser scanning, photogrammetry, drone mapping, crack gauges, motion sensors, and high-resolution imagery. These tools allow scientists to detect changes measured in millimeters or fractions of an inch. Features that might once have gone unnoticed until collapse can now be tracked throughout their development. In Yosemite, increased monitoring has revealed that many cliffs undergo continual movement. Some fractures open during the day and close at night. Others respond to seasonal temperature changes. Still others exhibit long-term trends associated with progressive instability. The Royal Arches crack belongs to this latter category because measurements indicate net widening rather than purely cyclical motion. Despite public concern, the existence of an expanding crack does not necessarily imply imminent collapse. Geological systems often evolve over timescales that are difficult to predict. A detached block may fail tomorrow, next year, or decades from now. The uncertainty arises because fracture growth is controlled by numerous interacting variables, including rock strength, moisture conditions, thermal history, geometry, and stress distribution. This uncertainty explains why park officials emphasize caution rather than prediction. Closing climbing routes and nearby access areas reduces exposure to risk while monitoring continues. Such measures acknowledge that the precise timing of rockfall cannot be forecast with confidence, even when instability is clearly present. The broader context of Yosemite's geology provides additional perspective. The Royal Arches crack represents only one visible expression of a vast fracture network extending throughout the valley's granite walls. El Capitan, Half Dome, Sentinel Rock, Glacier Point, Washington Column, and countless smaller formations all contain joints, exfoliation sheets, and fractures formed through similar processes. Many of these cracks are ancient. Some originated millions of years ago during uplift and erosion. Others formed more recently through stress redistribution and weathering. Most remain stable for long periods. A smaller number evolve into active rockfall sources. Half Dome offers a classic example of exfoliation on a monumental scale. Its curved profile reflects repeated detachment of granite sheets along fractures parallel to the rock surface. El Capitan similarly experiences ongoing exfoliation and episodic rockfall. These processes are not signs of geological failure, but manifestations of the mechanisms that created Yosemite's iconic scenery. The Royal Arches fracture differs mainly in the fact that it is currently observable during an active phase of development. Rather than representing a fundamentally different phenomenon, it offers a window into processes operating throughout the valley. The relationship between climate and rockfall has become an increasingly important area of research. Rising temperatures may influence thermal stresses within granite cliffs. More frequent heat extremes can enhance expansion-contraction cycles and potentially accelerate crack growth in susceptible areas. At the same time, shifts in precipitation patterns may alter water infiltration and freeze-thaw activity. Although no single climatic factor can be identified as the sole cause of the Royal Arches crack, the fracture exists within an environmental system where temperature and moisture continuously influence rock behavior. The interaction between climate and geology therefore remains an important consideration when evaluating long-term stability. From a geological perspective, The most remarkable aspect of the Royal Arch's crack may be its visibility rather than its existence. Similar processes are occurring across Yosemite every day. Countless fractures expand and contract with changing temperatures. Water infiltrates joints throughout the valley. Gravity acts continuously on detached slabs and pillars. Stress release remains ongoing as erosion removes material and reshapes cliff faces. Most of these changes occur too slowly to attract attention. The Royal Arch's feature has become notable because the rate of movement is measurable within a human time frame. A fracture widening from approximately 1 inch to several inches over a period of a few years provides tangible evidence of geological activity that is usually hidden from view. The crack also serves as a reminder that granite cliffs, despite their immense appearance, are not immutable structures. They are products of dynamic processes operating across timescales, ranging from daily thermal cycles to millions of years of tectonic and erosional evolution. Every cliff in Yosemite is a temporary configuration within a landscape undergoing continual transformation. Royal Arches itself owes its existence to this perpetual change. The sweeping forms visible today emerged through countless episodes of fracturing and rockfall. Future episodes will continue modifying the cliff. The expanding fracture near Superslide represents only the latest chapter in that long geological history. For now, monitoring continues as park officials track movement within the detached granite pillar. Climbers and visitors encounter closures not because Yosemite is experiencing an unprecedented geological crisis, but because a natural process is unfolding in a location where people frequently travel. The widening crack highlights the balance between preserving access to extraordinary landscapes and respecting the geological forces that created them. Viewed within the broader history of Yosemite Valley, the Royal Arches fracture is both unusual and entirely natural. Unusual because its growth has been observed, measured, and documented in exceptional detail. Natural because it reflects the same combination of exfoliation, thermal expansion, freeze-thaw weathering, water infiltration, gravity, and stress release that has shaped Yosemite's granite walls for millions of years. The widening fissure may eventually stabilize, or it may culminate in a significant rockfall event. That outcome remains uncertain. What is certain is that the crack provides a rare glimpse into the mechanisms that continue sculpting one of Earth's most celebrated granite landscapes. Far from being a static monument frozen in time, Yosemite remains an active geological environment where stone continues to fracture, cliffs continue to evolve, and the forces that built the valley continue their work today. The geometry of the Royal Arches fracture is another reason it has received sustained attention. Not all cracks within granite cliffs behave in the same manner. Some remain tightly closed and transmit stress efficiently across their surfaces, while others gradually evolve into distinct separation zones capable of isolating large blocks from the parent rock mass. The expanding fissure near the Superslide area appears to belong to the latter category. As the opening widens, the mechanical relationship between the detached pillar and the surrounding cliff continues to change, creating new pathways for movement and additional opportunities for weathering processes to act on the exposed surfaces. Once a fracture reaches several inches in width, environmental influences become increasingly effective. Water can penetrate deeper into the opening, exposing previously protected surfaces to chemical and physical weathering. Small fragments loosened from the fracture walls accumulate at the base of the crack, while repeated cycles of expansion and contraction gradually modify the roughness of the rock surfaces. These changes may seem minor when viewed over days or weeks, yet they represent a continuous transfer of energy through the rock mass. Granite is often regarded as one of the strongest and most durable rock types on Earth, and in many respects that reputation is deserved. Large granite formations can remain standing for tens of millions of years, while resisting erosion far more effectively than surrounding rocks. Strength, however, does not mean immunity to fracture. In fact, the immense size of Yosemite's granite walls creates conditions in which stress becomes concentrated along pre-existing joints and weaknesses. Over time, even exceptionally strong rock can fail when subjected to persistent mechanical forces. One of the defining characteristics of Yosemite Valley is the presence of extensive joint networks. These fractures develop through a combination of tectonic stresses, cooling-related contraction during the original crystallization of the granite, and later pressure release associated with uplift and erosion. The result is a landscape containing countless intersecting cracks, many of which extend deep into the cliff faces. Most remain hidden from view until erosion exposes them, or rockfall events reveal their existence. The Royal Arches fissure demonstrates how these ancient structures can influence modern geological activity. Although the crack itself became noticeable only recently, it likely exploited weaknesses that had existed within the granite for a very long time. Fresh fractures rarely form entirely independently. More commonly, stress becomes concentrated along pre-existing discontinuities, causing old joints to reopen, lengthen, or connect with neighboring fractures. The visible crack therefore represents only the surface expression of a larger structural system extending into the cliff.